In today's video, I'm going to explain the concept of continuous distribution and the idea of the probability that we observing an extra value is zero. So let's take a commonly used continuous distribution, which is the normal distribution, as our example. In continuous distribution, such as the normal distribution, the data can be taken on any value within a range, which could be infinite in both directions. So when we say that the probability of observing an extra value is zero, we mean that there are infinite possibilities with the value data that we can take, which make the likelihood of pinpoint one exact number is effectively zero. Instead of probability for extra values, we're talking about the probability of data point falling within a range. This is usually represented by the area which under the curve for a specific interval, which indicating that we consider a range of values but not a pinpoint number. In this normal distribution, which is centered around a mean mu of 0 with a standard deviation of sigma of 1, so this sign shade area represents the range within one standard deviation from the mean, which is this interval from -1 to +1, but doesn't capture the probability of observing an extra value, but rather than the likelihood of observing values within this range. This curve represents all possible values that the data we can take. Because the possible values are infinite, the probability is zero for the data we take at any specific value, like exactly 0 or exactly 1, the probability is 0. This y-axis shows the probability density, but not the probability. The probability of that value lies in with a certain range. It's represented by the area under the curve of that range. So for a normal distribution, it's about 68% of the data lies within one standard deviation of that mean, which is the sign area in this graph. When we try to sample from this distribution, we consider obtaining values near a target value, which is actually means sampling within a small interval around that value. So this is more practical and meaningful in continuous setting. Well, the pinpointing an exact value is impossible due to the nature of this distribution. So this visualization helps us to clarify that in continuous distribution, we're talking about the probabilities in terms of interval and the areas under a curve rather than the exact values. Let's talk about the concept of continuous measurement and the imposition inherent in the real-world data connection. So we can use a normal distribution also here to model the measurement of a male's height. The idea here is show that, well, we might record a height at 6 feet, but the actual value could lie within a small interval around this measurement due to the infinite precision of real numbers. In continuous data like measurements of height, there is no discrete step between the possible values. For example, from 6 feet to 6.00007 feet, the measurements are often reported with a practical precision, but the true value could be anywhere around the reported value. So the probability is considered over the interval rather than at any specific point, because the chance of measuring any exact value is essentially zero in a continuum. This is a normal distribution which represented the measurement of a male's height, which is centered around 6 feet with a small standard deviation, which is 0.05 feet, which reflect the typical measurement errors or variations, and the magenta shaded area, which highlights the interval around 6 feet from 5.95 feet to 6.05 feet, which show where we are expected the majority of similar measures to fall. The smooth curve of this normal distribution represents the continuum of the possible height measurement, so there is no distinct separation between the consecutive values, which highlighted the continuous nature of the real numbers. Although the recorded measurement might be 6 feet, but the true value could be realistically be any value within a small range around these measurements due to the infinite precision of the real number and the practical limitation of the measurement tools. This shaded area under the curve between 5.95 and 6.05 feet will show the probability density of the observing a height within this range, this area under the curve in this internal, which qualifies the likelihood of measurements which falling in these bounds rather than at any exact values. This visualization effectively demonstrates that when we're dealing with a continuous measurement, such as height, it is more meaningful to consider an interval of values rather than a specific point. So this approach acknowledges the limitation of measurement precision and the continuous nature of the data.